All right, so this video is going to be about all the different types of gauges you can use to inspect holes. It's not going to focus on just one like we did with calipers and micrometers. So this one's going to be pretty complicated. I may break this up into more than one piece depending on how long it takes me to get through the material, but we're going to be covering a wide variety of gauges. You can't even see all of them here on the workbench here, but basically, we're just going to be talking about how to measure the size of these holes. Not really anything to do with the location, but just all the different ways you can measure where the size is. So let's take a look at what we're going to cover. We're going to start off with gauge pins and Gonogo gauging. Go-no-go gauging. We're going to move on to the hole micrometer, 3-point hole mic. Seen here, very accurate. Next up, we'll do the telescope gauges and the small hole gauges. We'll do a tubular inside micrometer, and we're going to wrap it up with a dial bore gauge, a dial hole gauge. So if you ever use a dial bore gauge, you know it's a little tricky, but I think it's worth showing you because it can be very accurate for deep bores. And we also have this dial hole gauge. Works just like a small hole gauge, but actually has a dial feedback. So as I'm talking about this, we will talk about some other tools we've already looked at, calipers, as well as maybe I'll briefly mention how the CMM could help as well. So really any hole you do, you've got all these choices, and we're just going to show you the options you have. So let's jump into the gauge pins. So I've got a set right here. Let me take the lid off. So I have a set of gauge pins right here ranging from 251 to 500. If you look on the secondary camera here, you see how many there are. These sets are typically, or these gauge pins are typically sold in sets just like that one. And it'll range from about 11 thousandths in size all the way up to 1 inch. Those are the commonly available sets. You probably take 8 or 9 of those boxes to get a complete set. There's a breakdown from 0 to about 60, 61 to I think it's 125, 125 to 250, 250 to 500, 500 to 625, and it keeps going from there. So you can find these sets from a lot of different manufacturers. They will typically be sold in 1,000th increments, like the presentation has on here. Certain factorial sizes like quarter, eighth, 3/8, you can actually find them in increments of a tenth, and that is because many dowel pins come in those fractional sizes, and they typically be very tight tolerance. People typically like to use gauge pins to measure how big the dowel pin holes are. So if you check some online catalogs, maybe you can find some in 10,000th increments if you need them. You can get these above 1 inch, but they aren't made. They aren't mass produced, so you can have them custom made by a company. If you've got maybe a 2-inch hole that you're machining very, very often, very tight tolerance, and you want a simple go-no-go application, you can get these made in pretty much. I think I've quoted up to 6 inches before. I've definitely quoted 3 inches and 4 inches. So it is possible. When you are looking at a set of gauge pins, one thing to note is the accuracy level. So these gauge pins will come with a set accuracy. You'll see here on this chart, it goes from ZZ down to XX, and as it moves, starts as ZZ, like this pin here is a ZZ pin. It's the least accurately manufactured pin. So when these manufacturers are making pins through a grinding process, the accuracy of the pin after the grind is kind of determined by how quickly they do it, and repeatability and all that. And they can measure them and they can sort them. They can sort out the good ones from the not so good ones. Maybe the not so good ones get labeled as ZZ. Maybe they were running a little faster. Maybe the grinding process just took off a little too much or left a little bit too much. But ZZs will be accurate to the nominal stated variety. For example, this one says 0.490. So it could be within 2 10,000ths of 0.490 and still be an acceptable ZZ pin. If you have a class Z pin that drops to just 1 10,000th of an inch, if you get a class X pin, those get really accurate. They're 40 millionths within the nominal stated on the pin. And if you get XX, those are 20 millionths within nominal. So in most applications, I've seen most shops, ZZ is more than adequate for most applications, which is what most shops are going to have. And if you're working in a high precision, tight tolerance situation, you may want to go for X or Z. Just remember that that deviation I'm talking about is a total error. It's not a plus or minus. So it's not plus or minus 490. It's actually maximum 2/10 deviation from 490. And as well as classing them as ZZ or X or XX, they'll also be classified as plus or minus. So this entire set that I have off camera here that I showed you before is a minus ZZ set. And that means every pin is going to be at the nominal or smaller by a maximum of 2 10,000ths. None of them are going to be larger. People like it that way because they can use one set as a go side and another set as a no-go side. You can use your minus sets as the no-go. You can use your plus sets as the go, and guarantee that you're never going to be out of tolerance as long as the pins are in tolerance. That little 2 10,000th accuracy of manufacturing isn't going to affect you. So if you get a plus set, you're going to have plus 2 10,000ths maximum error. So I have a little chart here. You can compare plus tolerance, minus tolerance. You'll see it's pretty much the same. It's just one of them is going to be smaller, one of them is going to be bigger. So whenever you buy a set, pay attention to what you're buying. Make sure it's what you want. If you're not going to get both the plus and the minus, just make sure you know what you're getting. So I've mentioned that these pins are used for no-go gauging, and I haven't really explained what that is yet. So with a part like this one, and you want to measure the size of one of these holes, you're basically going to say, well, what size pin goes in and what size pin does not go in. So I'm gonna pull up the drawing, and we're gonna do a quick demonstration of this. So I've got, let's say it's this this bottom left hole here. On the drawing, that's calling for a 397 through all, and our our title block tolerance is plus or minus 5 thousandths. So if I've got 397 and my tolerance is plus or minus 5, my go size is going to be 392, and my no-go size is going to be 402. As long as my go pin and my no-go pin work, we're gonna be passing. So I'm gonna pull out the 392, which is here, and we're gonna slide that in. Let me switch the camera. So this is the 392 pin that I pulled out of the set. Slides very easily. It's a little bit loose, but it definitely goes in. And now I'm going to find the 402, and it doesn't want to start, right? I'm trying to push it in, and it just won't go. So right away, I know the hole passes the tolerance because the go pin went in and the no-go pin did not go in. I don't know how big the hole is exactly. If you watched a couple of the other videos, I've mentioned how no-go gauging won't tell you the exact size. Now I could keep pulling pins and try to find the one that just barely squeaks through, like this one. This is the 398. So it might have been drilled at 397. That would make sense, or 398. Doesn't want to quite go all the way. So let me grab the 397. And that goes pretty smooth. So this is about 397, between 397 and 398. I don't have another pin to tell me exactly any smaller resolution. So put that back. So that's how Gonogo gauging works, and it's a very quick way to tell if your hole passes. So the minimum size, as I have here on the chart, the minimum size is going to be your go size. The maximum size is going to be your no-go size. And you just see if, as long as one of them goes in and one of them doesn't, you're going to be okay. So when you are using gauge pins, one of the key one of the key things to remember is when you're dealing with a big set like this one here, you need to verify the size of the pin before you use it. And that is because these pins do wear. As you slide them in and out of a part over and over and over again, they will wear. If you buy pins that have a black oxide coating, you'll actually be able to see the coating wear away and know that the pin is getting smaller from wear. The pins don't wear evenly as well. They're going to tend to wear more on the ends where they get the brunt of the measurement, and less so in the middle. But so I recommend if you're concerned about wear on your pins, you get those black oxide ones. It'll give you a nice visual indication of the wear. The other issue is I've done it. Everybody I know has done it. They've grabbed a few pins from the box and they've returned them back to the wrong set, to the wrong hole. And I've also grabbed the wrong pins out of the hole. So I've seen other machinists do it too. You think you're grabbing the 392 and you're actually grabbing the 382 just because your mind's playing tricks on you. So what we recommend every time you grab a pin is to grab a micrometer. And I'm gonna verify my 392 pin. So we'll grab my mic. You'll see on here it says 392 minus. Hope you can see that. And I'm going to verify the size really quickly. And with my micrometer, if you've seen our micrometer video, you should know how to read a vernier scale. But if you want to go check that out, go right ahead. So I'm about 391 and maybe 8/10. So this might be at the extreme. It's actually at 7/10. So this might be a little bit out of spec, this pin. And that's good for me to know, before I measure the hole. Is that going to be a problem, right? It's a little bit out of spec, maybe a 10th out. It could be the micrometer might be a 10th off. When we did the micrometer video, we talked about how it can be very difficult to verify those. Let's verify our 402. Make sure that it had the right. It's the right size as well. All right, so our 402 also a little bit small. Maybe we'll check the vernier scale. Oops. Yeah, maybe also. So maybe it's this micrometer's off by a 10th. Let's take a look real quick. A little practice. Looks pretty good to me. So either way, I'm not too concerned about it with a plus or minus 10 tolerance and a class ZZ pin. But when you start to use your pins, these have been used quite a bit. When you use yours, just remember to double check the size. Make sure it's what you think it's going to be. All right. Oops. All right. Let's fix that real quick. One last tip. When you are calibrating these or checking these, it can be helpful to go all the way around in a couple places just to be sure. That's more useful for calibration because it could be worn in one spot and not another spot. So check axially and check around. When you're just using them, as long as they're still within calibration, I think it's fine to just check one or two places, make sure it's the right size. So now that we're mentioning calibration, you kind of have two options. You can send them out and the calibration vendor is going to verify their diameter as well as their shape. They've got some optical equipment that can do that very quickly and very accurately. They will usually inspect every single pin and you will get a report back on every single pin. If, for example, if 4 or 5 of them, the ones that get used the most, have worn out of tolerance, you'll get that noted on the list that, most of them passed, but 4 or 5 didn't. They will note that. When you do this in-house, you're not necessarily going to be using the optical equipment. Depends on if you have it and if your procedures are set up. But I've seen a lot of places, they take a calibrated micrometer that's traceable, and go ahead and watch that video if you haven't, if you're not understanding what traceability is. But as long as you have a calibrated traceable micrometer, you measure every single pin. It's a little tedious, but you just check one after the other, and you'll be done pretty quickly if everything's in spec still. There's no real adjustments. You don't have to really record what you adjusted it to. So another way I've heard of a shop, one of my former employees gave me the idea that if it's a black oxide pin and you got a bunch of these pins where the black oxide has worn off, well, you already know they've probably worn out of tolerance, and you just replace those, and you can put that in your calibration routine to check for the wear on the black oxide, and just have them calibrated once when they have the black oxide on, and then visual after that. But I would still confirm with a micrometer to maintain traceability. And really, this is going to come down to what your company defines as a policy. You certainly have a few options, and I encourage you to discuss your options and think about what works for you. One of the reasons I'm bringing it up is there's going to be close to 1,000 pins in a set, so it gets time consuming and it gets expensive if you're going to send it out. Some places will do it for $1 a pin, not too bad, but for some shops that may be expensive, and then you've got to wait for them to come back. So it's up, think about it, talk about it, look at your quality manual, what your policy will allow, what makes sense for your company. That's if you're in an ISO 9000 shop, that's one of the key things about ISO 9000. Just be thinking about what you're doing and justify it. All right. So that's pretty much it for pins. I will say, one more thing. Gonogo gauging is a quick, very accurate way to just check holes very quickly. I recommend you, if you're going to be checking a lot of holes the same size, have a set real close by, grab the no-go, boom, boom, you're done. You move on. It's going to be it's going to be one of the fastest things we do besides automation. So one of my favorite gauges. Now we're going to move on to the hole micrometer. This is another micrometer I really like. It's very accurate. When we've talked about OD micrometers in another video, we talked about how this is about 1/10,000th or 2/10,000ths of accuracy error, which is pretty great. And the hole micrometer is going to maintain that, really. It's going to have maybe just a slightly worse accuracy, but not nearly as much as some of these other gauges we're going to go over. So it's very accurate. It's great because it self-centers. That's one of the easiest ways to use it. It's got that vernier scale, so you're going to get a lot of accuracy out of it. This one's 2/10,000ths deviation. That's pretty accurate. A standard micrometer gives you 1/10,000th. This just gives you a scale in 2/10,000ths. One of the downsides, one thing you need to be aware of, I should say, is that when you're checking the bottom of a hole, as I have in this picture here, bottoms of holes, as I've mentioned, will tend to have a radius or some other manufacturing method left behind. And you want to be careful to not have your anvil registering in the radius. You want to be above it. You don't want to be measuring the diameter when you're grabbing the radius, because it won't give you an accurate reading. Hopefully your design of the hole counts for that radius, and whatever machining mark is going to be left behind, whether it's turned or bored or some other method. But just make sure you're above it. And if you're not sure, I would say drop it all the way down to the bottom, lift it a little bit back up, or check in a few places throughout the length of the bore, and just verify that it's not drastically smaller at the bottom. So we're going to go through pretty much how to use this. The first thing you're going to do is you're going to verify this thing on a setting ring. When we talked about using the OD micrometer, we talked about checking these on a Joe block or a micrometer standard that comes with it. For these hole micrometers, you're going to have a ring. You're going to have to maybe purchase the ring separate from the micrometer. They don't always come together. They're a little bit pricey, so they get sold separately in case you don't need a ring, but you want another micrometer. Or maybe you need a ring for your micrometer. So first thing we're going to do is I'm gonna go through these 5 steps here. Let me just review them real quick. All right. So we're going to go through these 5 steps, and we're going to see if this is in calibration first. So I have a 1-inch, practically 1-inch ring. It's about 40 millionths smaller. And I have a micrometer whose range is 0.8 to 1 inch. So at the maximum of this, I should be reading 1 inch. And we will double check. So this has a ratchet, and as I'm bringing it into the hole, I can't really see it with my hand in the way. As I'm bringing it into the hole, I'm kind of jiggling everything so that it self-seats and centers. It is possible to kind of have it at an angle, and then you'll start to hear the ratchet go, but you're not self-centered yet. So I'm just jiggling it, letting it do that. I got about 3 clicks, and then we're going to bring it up to the mic, bring it up to the camera, and looks pretty great to me. It looks like 1 inch exactly. I probably don't need to adjust the calibration. If I do need to adjust the calibration, we're gonna unscrew. There we go. This screw there, and this is how we're going to adjust the calibration. So I'll do that in a little bit. But for right now, this is set for 1 inch. You can see that there. So now that it's good, we're going to measure this bore, and according to the print, once again, go to the Pragmatic Metrology website if you need the print. So it's supposed to be a 970 through bore. So gonna bring this in. Again, I'm kind of shaking it so that it self-centers. I'm starting to feel resistance. I'm gonna do this near the top of the bore. I got about 4 clicks. And let's take a look at our reading. So we're gonna have to learn how to read the vernier scale, right? There's another video that I've talked about this. I've talked about this at the micrometer video. So I'm just gonna read this one. Reading this is just like any other micrometer. You're gonna have to count the lines. In this case, I can kind of start to see a line, right? We've talked about this before, but I haven't reached 0 yet. I'm still approaching 0. I'm between 20 and 21. So I'm gonna say I haven't reached that line yet, even though, man, it is pretty clear, right? I don't even know if you can see it on the monitor, but there's a line just underneath the thimble here. But because I'm between 20 and 21, I haven't reached it yet. When I get closer to 24, 0, and then 1, I know I've reached it. So that's one of the tricky parts of reading the vernier scale, is when you can see those phantom lines. So if I can't see it, I know I'm just shallow of 1 inch. So I'm definitely at about 0.950. And then I'm going to add, from 950, I'm going to add 20. So I'm going to be at 970. And then I'm going to add the last bit, which is wherever these lines for the 10,000th scale line up. So I'm going to pull it off camera so I can see it clearly. And I'm going to say the 4 10,000ths line lines up just perfectly. So check out the camera feed here. If it's not showing up well on the TV, I'll try to get it on there. But the 4 10,000ths line is looking good. So we're going to say that it's 0.970 and 4 10,000ths, 0.974, 0.9704. And just for the sake of argument, because we're using this gauge for the first time in this video series, let's see what our trusty caliper says. So I got 0 there. This should just get us in the ballpark. So it's saying 968, which is in the ballpark of the 970 we just got with the micrometer. And we know the micrometer is a more accurate gauge. So I just got 970 and 4 tenths at the top. All right, I'm pretty much right back there. And what I recommend you guys do is when you take a measurement, you see where that foot is. Well, there's some pockets where you're not measuring it, and this hole could be out of round. Given the size of it, given the material, I definitely expect to see a little form error. So I want to look for that. So I'm going to rotate it about, what is that, 30 degrees, 60 degrees? I can't do math. To the point where I didn't have any feet. And we're going to double check our reading. And it's pretty consistent. Say about 970 and 5 tenths now. That's pretty good. So I've done 2 at the top. I'm going to move to the bottom and get another couple. And we're about 970 and 3 tenths. So we're seeing a little bit of difference, but not much overall. It's a very well machined. There we go. I have a little phantom clicking, but here I'm at about 970 and 3 tenths. So I always recommend twist this thing around to a few angles as you get larger and larger bores. Maybe you want to check more than just a couple of rotations, and then up and down as well. Up and down the length of the shaft, because every piece of this bore needs to be in tolerance. It can't just be a tolerance at the top and then it tapers small at the bottom, or the other way around. It can't be in tolerance at the top and tapers big at the bottom, or it's out of tolerance in the middle, but it's fine at both ends. I've seen everything, so I recommend check the entire length of it. All right, fix that. Sorry about this. Okay. So I didn't need to calibrate this one, but I will show you how to do it. So as I mentioned, there's a screw. There's a screw on the side, and whenever you loosen this screw, it allows the sleeve to free float. So all right, so we'll flip over to the monitor. When you loosen this screw here, this sleeve with the engraved 1 deviation equals, this will free float in this direction back and forth, and that'll allow you to set your calibration. So I'm going to intentionally move it out of spec and then move it back. Here we go. So let's verify again that we're good right now, and then we're going to mess it up. All right, we're looking pretty good. Maybe a hair above 0 there. So now I'm going to loosen this screw. And what I want you to pay attention to is not only can I go left and right, I can go left and I can go right with the sleeve. I can also go in and out. So I can basically move how I can see those lines. And that's one of the trickiest parts about using this style of micrometer is whenever somebody moves the sleeve in or out, well, it can affect how many lines you can see. And maybe I'm trying to get it perfect there. I can just barely see that 0 line. But when I rotate it 25 thousandths or close to a 25 thousandths, it affects, can you see that next line or not, right? This is what I've talked about a few times. So pay attention to that. I've seen a number of times, I've done it myself, where I accidentally set 0 and you can actually, you see that second line very clearly. And a lot of people end up misreading it by 25 thousandths or 50 thousandths, depending on the style. So be very careful. I'm going to try to be very careful. And it can be a little tricky to do everything all at once, where you've got to hold down the sleeve in both directions. I hope you can see this. It looks great on the second camera. So I'm going to try to do it right there. I'm going to screw this in. Oh, there we go. Okay, I already moved it, but all right. Oh, moved it again. I think I'm okay. See, when I go to tighten it, the sleeve moves. So I'm gonna have to set this down and really get a good look at it so that I can do this right. All right. Now I've got it tight. I don't actually have it perfect on 0, but I need to double check this, because even though it reads what it reads right now, as soon as I loosen it and I go to check it again, it'll probably read a little different. So let me check this. All right, it actually reads pretty good now, I think. I think I'm happy with that calibration. Okay, so if you're ever out of calibration, you're gonna have to loosen that sleeve, manually twist the sleeve here and put it back. And it can be a little tricky. One last thing, just like any other micrometer, when you are measuring a hole, as long as you get nice pressure and click it in, you can wiggle this thing out of the hole, assuming the hole's not tapered, and do your reading. It won't move, right? As long as you're gentle and twist it out, this won't move. Shouldn't scratch up your part, although it might. These feet can be kind of sharp and on the edges. So if you're ever in a situation where you can't see what you're doing because it's still in the machine, you can just slide it out very gently. All right, we're gonna do one more gauge. And call this video. We're gonna do the rest in the next video. So we're gonna start off with the telescope gauge, and this is another. This is the first. Let me think about this. Yes, this is the first transfer gauge that we've really talked about in this video series. If you're watching it in the recommended order, the telescope gauge is a transfer device because it actually has no markings anywhere on here. You're gonna put this in the, you're gonna put this into the, demonstrate this, into the hole, and you're gonna lock down these sides when it's in the hole, and then you're gonna measure across it with a micrometer. That's why I have a couple micrometers here. So, for example, for this part, once it's in there, I can lock it down, pull it out, and now I can measure across this distance with a micrometer. So it's a transfer measurement. It's not a, there's no markings on here to tell me how far apart the anvils are. So telescope gauges, there's more than one transfer device we're going to talk about. Telescope, it registers on 2 points, and it does not self-center like the hole micrometer did. The hole micrometer not only sort of self-centered on the part, but it also kind of axially centered itself, which is what this will not do. You can actually, on the diameter, you can get this thing to wiggle into the diameter with a telescope gauge, but axially, that's going to be up to you to find the right axial fit. The anvils here are spring loaded. Some anvils or some telescope gauges, both of them will be spring loaded. Other telescope gauges I've seen, only one of them is. So just keep an eye out for that. This knob here at the top of the gauge, right here, it's what locks it in place. So if you saw me before, when you lock it in place, you twist this knob at the top, and then it won't spring out. So your method for doing a telescope gauge, I'll demonstrate that here one more time. So you're going to pick your gauge that's in the right size. You're going to have a range of options, right? I have some small ones here, and I have some larger ones here. So right, you have a wide range of options. Oops, there we go. So they're all marked what size they do, so you don't have to do too much guess and check. So when you drop this in, you're going to have to manually squeeze down the anvils to pop it in there. And then I want you guys to kind of sweep it and twist it until it feels like axially, you're on the right diameter. Okay, so kind of rock it, and then when you feel like you're already kind of self-centering on the diameter, you're going to have to axially. Oops, I went a little too far, and now I really jacked it up. Okay. I won't do it inside, but you're going to have to make sure you're axially correct. Okay, so this thing is on the circle. This thing's going to be easy to self-center, but you're going to have to, for this is what you're going to be working with. So sweep it, and then try to feel for that high and that low, and you'll kind of feel when it transitions. So this isn't the most accurate because you don't have any feedback other than your feel. But when you think you're there, you're going to lock it down, and then you can rotate it this way, drag it up and down. If it's too loose, you'll feel it. It'll just be banging around way too loose, and that means you set it you closed it at the wrong size. If it's too big, you won't be able to drag it out as you pivot it. It'll interfere because it's too big. So go ahead, and this is a pretty good, nice slip fit that I can feel, right? I can sense that that it was a good measurement by the way it's slipping through. So practice this a few times. It doesn't happen the first time to get that feel. But once you do have that feel, we're going to measure it across it. So we're going to grab a calibrated micrometer, and we are going to measure across the anvils, and that'll give us our reading for the diameter at that spot. And as you're doing that, again, this becomes a pivot motion, back and forth, in and out, right? So I am kind of rocking it. I've got it registered on the bottom here. I'm putting the force here, and I'm rocking it. Oh, you know what? I moved it a little bit. I put a little too much force. So Watch out for that. I'm going to do this one more time. All right. Squeeze this in. I'm twisting and letting it find center. Locking it, and that might be too loose. I can feel it wiggling around a little too much. I'm going to do it again. All right, that feels pretty good. So let's do this one more time. I'm going to register on the bottom, and I'm kind of rocking it through. I'm trying to feel when it slips, just slips through. Right now I've got a little too tight. I can't move it anymore. But when it just barely feels like it slips through, and you can kind of rotate it this way, just like when you're doing a micrometer calibration on the standard. When you can twist it this way and it looks good, doesn't flop around, you've got a good reading. So we're going to lock this in place. And let's see, I'm at 1 inch, about 374 and probably 9/10 on the scale here. So 1.374 and 9/10 reading this vernier scale. And once again, we're using a new gauge. I'm going to grab my trusty caliper, make sure I didn't do something wildly wrong, like read the vernier scale wrong. So caliper, not as accurate as the micrometer. It's debatable. It's kind of debatable if you use a direct caliper measurement or you use a transfer telescope gauge. Some people just are not skilled enough with this to say it's more accurate than the caliper. One of the advantages is that I can get a lot deeper with my telescope gauge. Like I can go all the way through, but with a caliper, you're really limited to the depth of those inside jaws. So you can't get anything deeper than the inside jaws. All right. So I just demonstrated. Sorry, guys. I just demonstrated this technique, but if you need to review it, just pause the video and take a look right here. So we're gonna, I said we're gonna stop at the telescope gauge, but we got time for one more. We're gonna include the small hole gauge because it is actually very similar in concept to the telescope gauge. It's another transfer device. Put that away later. So a small hole gauge, instead of being a telescope shape, it's basically got these flexible diameters. Oh, sorry. It's got these flexible diameters here. So as I twist the knob back here, it's spreading. I think I've got too many gauges for the camera to focus. Let me move a couple of these off. All right, should look a little better. So as I'm twisting back here, I'm spreading that bar, that diameter. So when you do that in a hole, eventually it's going to stop at the size of the hole. So let's do a quick measurement on this hole. We have to find the gauge that fits. Oh, actually, oh yeah, this one will fit. So right now it's too loose, right? This anvil on the inside isn't pushing out enough. So as I move that anvil away, it extends it. So let me do that in a small hole. Show it this way. So as I twist, that anvil is getting bigger, and eventually it's stuck. I can't move it anymore. So I went a little too aggressive, and I'm gonna rock it around and try to make sure it self centers just a little bit. There we go. Feels pretty good. And I'm gonna drag it out. And once again, we use our calibrated micrometer to measure across the anvil. We measured this earlier. It was supposed to be a 397 hole with a plus or minus 5 tolerance. So I'm rocking this through the anvil, and when it just barely slips through, I know it's at a good distance. So let's take a look at this. And I'm reading just a hair over 0.4, maybe 0.4 and 0.2, which is close to what we got with the pins. I think we got 397 with the pins. So obviously I twisted this a little bit and ended up spreading this while it was still inside the hole. And when I popped it out of the hole, the anvil spread a little bit more. So that's one of the trickier things. You got to have a really, really light touch if you're going to be using the small hole gauges. I don't particularly like them. I hardly ever use them. For one reason, I've got pin gauges. So if you've got pin gauges, there's almost no reason to use the small hole gauges, because you're going to have pins of 1,000th increments, which is probably going to be accurate enough for what you're inspecting. But if you need to, here's a kind of a diagram of how it works. On the left side, the anvil is completely extended. There's no tension being pushed on that diameter that spreads across. And as you bring the anvil in, it spreads out. So pretty straightforward gauge. Works just like telescope gauge. So just give you a preview. I'm going to pause the video here and take a quick break, but why don't you watch the next video, and we're going to go through all these other slides. So I want to thank you guys for watching this video. And I want to encourage you to visit the Pragmatic Metrology website, where I've got other videos on all sorts of gauges that will help you with your careers. And I want to thank the Laney Machine Technology Department in Oakland. The Laney Community College provided these parts and a lot of these tools here. And they've got a great program that covers manual machining, CNC machining, inspection, mechanical drives, all sorts of classes, computer-aided design, CMMs. They've got a great manufacturing program. So if you're in the Oakland Bay area, please check out the Laney Community College. They've got certificates you can earn that will help you in your career. It's not just the associate's degree, but you can also get some certificates in machining, apprenticeships. They have all sorts of support there. So please check it out, and please check out pragmaticmetrology.com for more videos, more training, and more resources. And I will continue this series in the next videos. Thank you.